that. Okay, so what happened is that I see, yeah, I forgot to record the first part. So indeterminate forms of limit, it's just gonna apply for these 7 forms, and every single step that you use the Hospital rule, you just have to plug it in and check it back, because in many of the, I wouldn't say exam yet, because I think they learn after the quiz, is that they just continue to do the Hospital rule until it gives them like a just like numbers, and that's usually is not the case. In some of those steps that they apply the Hospital rule and without checking, they actually change the answer of the solutions, and this is not right. So by principle, because the Hospital rule cannot be used if the limit is not in one of these 7 forms. And so yeah, when we have one of these 7 forms, what we do is just, if we have a quotient like these two, then we're gonna apply the Hospital rule by making sure that first your f and g, so numerator and denominator, are differentiable, and the limit, as I say, you plug in, it has to be in one of these 2 forms, and gx have to be different from 0 near a, so gx have to be defined at a. It's kind of like another way to say it. So then you can test that limit is going to equal the limit when you take derivative of both the numerator and denominator. Then we have, if it's in the product form, like 0 multiply infinity, then you just make it into quotient by using this expression, like, because like just like a change of algebra. If it's a difference, then you again, like all of these technique is just try to make it into the quotient first before you can take the Hospital rule, because the Hospital rule is in the form that you take the derivative of both the numerator and denominator, so you have to make it into a fraction first. So if you have a difference, you make it into a quotient by common denominator conjugation. So common denominator is more like if you have like 1 minus 1 over a minus 1 over b, and you try to make it into the same of a and b. So you just multiply b here and multiply a here, so it's b minus a, some things like that. And then, or you multiply the conjugate of that, or if you have ln minus ln, and this is like a property of ln is that it's like maybe it's here a and b, then it's going to equal ln of a over b, and now you have a fractions. If you have a power like 1 to the infinity, 0 to the 0, or infinity to the 0, you're going to make it into product, then quotient. So first product by, say, you take, so you have fx to the gx, you're going to put it in the form of e to the gx multiply ln of fx. So basically you just take e of this, but then you have to take ln of, so say you take e to the ln of this thing. And because to the property of ln is that when you have something to the power inside the ln, you take that power outside. That's why you get this thing. So with those kind of like manipulations, then you can put it into the quotients and then use the Hospital rule. Now let's get started with the first example. So here it looks like we're going to have a power, but first of all we have to plug it in to make sure that it's in the form. So you plug in if you plug in x approaching 0 plus, then what you're going to have is that it's going to be 0 to the ln of 0 plus is negative infinity. And so this, and then is 0 plus or 0 third is the same thing. So you're going to have 1 over negative infinity is 0 to the 0. So now you can use the Hospital rule. So here another thing that I would recommend is that you guys should have like an H here, or like something to denote the fact that step you use the Hospital rule. Because sometimes when you stop using the Hospital rule and you come into like doing algebra and manipulations to get the final answer, because like that fraction is no longer in the indeterminate form, then these step of like noting down helps you check back, especially when you have in the exam like maybe 25 of these stuff of limits, and or like 5 or 10 of that, and then some series, and then when you come to check back, like most of the time you couldn't keep track of what you're doing. So let's do you're gonna take limit of x approaching 0 plus. Now take Oh, not the L'Hopital rule yet. You have to put it in the product. Sorry. You have to put it in product form. So you're going to have e to the 1 over ln of x cubed multiply ln of x over 2. Now you can take this e outside and take this limit inside. So you're going to have e limit of x x approaching 0 plus ln of x over 2 over ln of x cubed. Now you're gonna have, so what I usually do is that I just do the limit separately because I don't want to like rewrite the e all the time, and it just later on you're just gonna plug it in. So now if you plug in 0 plus, this is the form of infinity, negative infinity over negative infinity. So what you're gonna do is now take derivative of both the numerator and denominator. So derivative of ln of x over 2 is going to be half over x over 2, which is going to be x, which is going to be 1 over x. And then for x cubed, it's going to be 3x squared over x cubed, which is going to be 3 over x. So it's going to give me 1 over 3. Therefore, I can just plug it in, which is going to give me e to the 1/3 or cubic root of e. So again, the step is pretty self-explanatory. I feel like this section is easier when we can put it into approach like this. So yeah, that's the first example. Before I go to the next one, is there any question? Okay, so what did you do in the middle step? Like which middle step? Oh, so like when I go from the bottom? Oh, so from here to here, yeah, you just do the L'Hopital rule. So, and then after that, you have 1 over x over 3 over x, so you can simplify it to 1 over 3. Does that make sense? Okay. Okay, so I'll go to the next example. So in this, again, you have to plug it in. And clearly, when you plug it here, you're going to have infinity minus infinity. So the way that I'm going to do it, and this is a difference, so infinity minus infinity. So you know the first step you have to do is take make it into a quotient. And in this case, I would say we have three approach. We have conjugations, we have make it into the same denominator or ln. But here, the only thing that we can think of is conjugation. So we're going to do limit of x approaching infinity. So you have square root of x squared minus 10 minus x plus 2. Now, when you multiply the conjugation, you have to multiply it in a special one, which is going to be like square root of x squared minus 10 plus x plus 2 divided by square root of x minus 10 plus x plus 2. So this one is kind of like another way for you to write 1. So for, I think, yeah, for the new people who just joined us, please put your PSU email in the chat room as well. So here, after we have this fraction, so what you're going to do is just multiply this part and leave the numerator. Give me a second, I'll note down the 51696 and then aka 570. Okay, cool. So we're gonna have here, so the denominator is gonna be square root of x squared minus 10 plus x plus 2. And then you multiply numerator together. So in this case, it's you have this part, multiply this part, and this is where we're gonna use the special expression a minus b multiply a plus b is equal to a squared minus b squared. So I would say this is kind of like what most of us should know before we take calculus 1, because I think you guys have to like satisfy some of the requirements to actually take 140 and 141. So this is kind of like in the, I think the elementary algebra that we have to know. There's one more people who just joined us, but can you please put your PSU email in the chat room? Yeah, so here A is going to be square root of x squared minus 10, and B is going to be x plus 2. So you have A squared minus B squared now. So it's going to be x squared minus 10 minus x plus 2 squared. So now it's going to be limit of x approaching infinity. So x plus 2 squared, just here I'll just write down as x squared plus 4x plus 4 divided by square root of x squared minus 10 plus x plus 2. And so now you're going to have limit of x approaching infinity, negative 4x minus 14 divided by that. Okay, now it's time for us to plug in to say if we can use the Hospital rule. So now you plug infinity in. Here you're going to have negative infinity over infinity. So this is negative infinity over infinity. So I'm going to use the Hospital rule here. Limit of x approaching infinity. Now take derivative of both the numerator and denominators. You're going to have negative 4 divided by 2x, no, just x, over square root of x squared plus 10 plus 1. Now you plug in infinity. So you're going to have negative 4 over this fraction plus 1. So you have to figure out what this fraction is going to equal as x approaching infinity. And very clearly, if you look at the biggest power in both of them, you have x, and then you have square root of x squared, and x is approaching infinity. So when you take this fraction can be fine, I'll write it separately here. Limit of x approaching infinity, x over square root of x squared plus 10. And I minus 10. Oh. Minus 10, minus 10, minus 10. So what happened here is that this is also one of the special things that I want to note in this example, is that there is a difference if x approaching negative infinity here. This is because if x is approaching negative infinity, when you take it out of the square root, you're going to have x over 1 minus 10 over x squared. This is for x approaching infinity. But if x is approaching negative infinity, what you're going to have is you're going to have x here, and then negative x, square root of 10 minus 1 over 1 minus 10 over x squared. So for that particular purpose, this limit is going to become negative 1, and this one's going to be 1. So there is a difference when x approaching infinity or negative infinity. So in this case, I see if you have these kind of problems, like if you have first power here, and then this is square root of a square, which is also the first power, don't just assume the fact that it's just their coefficient divided by one another, like 1 divided by 1 is not right. You also sometimes have this negative here, depending on where your x is approaching. So here, when you come into this part already, so you can cancel out the x, because x approaching infinity is not 0, so you can cancel it out. So what you have left is going to be 1 over, so I'll write here, limit of x approaching infinity, negative 4, 1 over square root of 1 minus 10 over x squared, plus 1. Now, for 10 over x squared, when you plug in x approaching infinity, 10 over x squared should approach 0. So you have negative 4 over 1 plus 1, which is negative 4 over 2, which is going to give us negative 2. So there is a lot of things going on in this example, and a lot of things I want to show you guys, because a lot of people forgot how to take conjugation already. So I want to remind that one. And then when we start to have a bunch of like things together and we take the Hospital rule, there's also some notes regarding taking x out of the square root. So, is there any question with this example? DRV5. So do you think, so you took the derivative, and then what happened after that? Okay, I took the derivative, but here, you stop here, right? From this step, give me a second. From this step, right? So here you didn't take the up here you don't take derivative at all. The only step that you take derivative is this step. After that, you have this limit, right? You have -4 and 1, which is pretty easy. It's just number. But then you have this small part here. If you plug in infinity, you're gonna have infinity over infinity. But from practice, like I think in 140 we also deal with it, but a lot of us forgot, is that we have x over square root of x squared minus 10. If you look at the highest power of the numerator and denominator, there's one short way for you to find this limit. So it's kind of like simplify the thing instead of, because here it's not okay to use, like it's not worth it to use the L'Hopital rule again. But from here to here, there's two ways. You can do L'Hopital rule with just this fraction because it's infinity over infinity. Or you can do the way that I did, is that I'll take the highest power of them out of the square root. Like here you have x and here you have square root of x squared. So the highest power is just going to be x. So I take the x out. But if you do my approach, there are two things that you have to note when x approaching infinity and x approaching negative infinity. So this is a negative. Yeah, so when you have x approaching infinity, when you take the x squared out of that square root, it's going to be x. But if you have x approaching negative infinity, and you take the x out, it's going to be negative x. So that's the only difference if you go with my approach. But here you can also do the L'Hopital rule with just this small fraction because it's infinity over infinity. Is that clear of how I get it? So after you do this approach, you're going to get back to this part, this step. So if it was 4x squared, the fraction would be 1/2. Yeah, that's correct. When x approaching infinity, of course. If x approaching negative infinity, it's going to be -1/2. Okay. So that is all good. Then I'm going to go to the next example. So this is like a very odd one, but it's a very important one to me, as what I've been saying throughout, that you have to check the L'Hopital rule. So here, when you put, a lot of my students just like look at this and they're like, okay, what the hell am I gonna do? So, and then I'm like, they're like, and then they're in the L'Hopital rule, and then the first thing they're like, okay, maybe I can try the L'Hopital rule and see if it'll give me something. Well, it does give you something, but it's not the right answer. What happened is that they forgot to check if it's applicable for the L'Hopital rule or not. So when you plug in theta equal pi over 2, you're going to have 1 minus sine of pi over 2. So 1 sine of pi over 2 is 1. So 1 minus 1 is 0. In the denominator, cosecant of pi over 2. So note the fact we have cosecant is equal to 1 over sine. Sine of pi over 2 is 1. 1 over 1 is just 1. So 0 over 1. So this entire thing is just going to equal 0. So the note here is that do not just use the L'Hopital rule blindly. Yeah, and just like try to make it capital so that everyone know the fact that check, please check it every single step you want to use the L'Hopital rule, and then check it after you finish as well if you want to proceed with more the L'Hopital rule. So yeah, that's all I have for 6.8. So it's pretty explanatory. Just try to make it into a quotient. No, first check it if it's in an indeterminate form, then put it in the quotient form, and then use the L'Hopital rule. After that, check it back again if you continue to use the L'Hopital rule. So then we have something called improper integrals. So improper integrals is where, kind of like another way to say it, is where you have your boundaries of the integral related to either to infinity, or it relates it to some of the discontinuity in your, or your like maybe like fraction inside the integral. So something inside like here, it has some discontinuity on the interval that you specify. So this is one of the mistakes that I kind of make a mistake when I calculate a number in my head last week. But yeah, it should be. We're gonna learn about it not last week, the week before that. Yeah, but then this is what we're going to learn. So there are two types of improper integrals. Type 1 is where you have the boundaries relating to something with infinity. So say you have three types here, and the first thing you're going to do is just rewrite as limit of t approaching maybe infinity or negative infinity, and replace that boundary of infinity with t. Then you just continue to do like regular, just then take then you just continue to take integration based on what you learn in midterm 1. Yeah, sorry, like the thing you learn in midterm 1 hasn't finished yet. You're gonna still see it in series as well when you use the integral test. But yeah, you just normally take integration with the boundary be a and t. Remember, don't forget this limit as you copy down the integral. And then when you plug in, then you do plug in. Then you have just plug in the value of t. We still keep that limit. And then you're just gonna figure out like what is that fraction is gonna give you. And so the highest thing that you can be asked in this session is that you can be asked something where you have to take this like improper integral with infinity. Then when you take integration and all of that, which use material in midterm 1, then you're gonna have to find the limit. And the highest thing that they can ask you, like the hardest thing, is that you're going to figure out that limit is going to be one of the indeterminate form. So then you're going to use what you learned in 6.8. It's going to become a long problems, but it's going to be like the highest thing, and it's, in my opinion, is like the best way to ask this. So make sure that you understand every single aspect of the materials that you're learning. So yeah, so those are the form that you're going to write it. If the limit exists, then we say the integral converges. Some of the thing that you commonly seen is this type. So when you have the integral from 1 to infinity dx over xp, is going to diverge if p is smaller than or equal to 1 and converges for p bigger than 1. And you can use this in the exam. Yeah, so use this. You can use this part in the exam. Then you have type 2. Type 2, as I say, is that when your integrand, so the thing inside, have some discontinuity on the interval, like say from a to b that you specify. So there's three cases. It's either discontinuous on one of the ends, and then it's discontinuous as one of the number in between. So if it's discontinuous in between, then you can put so say if you have the integral from a to b of something, you can break it down to from a to c and c to b. But this big integral that you're given is only converges if most of the complementary integral are convergent. So yeah, so it's only, then we have something called a comparison theorem. So if you have f and g are two continuous functions, and g is smaller than f and bigger than 0 for x bigger than a, then you have the integral from a to f. If a to infinity of fx dx, if it's convergent, then gx is convergent. So basically it's saying if the big thing is convergent, the small thing is convergent. Remember, it has to be positive. And then if you have the small thing, it's divergent. The big thing has to be divergent as well. So the tricky thing here is that you have to remember the direction. So if just the way that you think about it, so the way that I make sense out of this and kind of like remember it as well is where you have, if you have a big one already converge, the small one has to converge. It cannot get bigger than the big one. So, and then if you have the small one already go diverges, so it already blow up, then the big one has to also blow up. It cannot just converges because something smaller than that already blow up to a big number. So that's improper integrals. So let's get started with our example. Let's see how many examples we have here. So we have 3. So let's go first to example 4. So first, very clearly, you can see the fact that, give me a second, is where your boundaries related to negative infinity and infinity. So the first thing we're going to do is that we're going to have rewrite it first in limit of t approaching negative infinity from t to 0 of 2 to the x dx, and then limit of t approaching infinity 0 to t 2 to the x dx. Now I'm going to find each of them individually because remember, when you break it down, you need both of them to be convergent so that the big thing is going to be convergent. So I'm going to find infinity first because I don't want to deal with negative number yet, but if that one is also convergent, I'll have to deal with it soon. So what we have here is now, so let's see if you guys still remember this. So what is the integral of 2 to the x dx from midterm 1? What is the integral of, 2, CTS is continuous, and then multiply. The integral of that is 2 to the x over ln of 2, not multiply. Oh, maybe I asked you guys what's the derivative of that. Okay, yeah, maybe it's just me making a mistake then. Yeah, the integral of that is 2 to the x over ln of x, or the derivative of that is 2 to the x ln of 2, which is, oh, sorry, ln of 2, not ln of x. So yeah, you're going to have from 0 to t. Now, if you take the constant out, which is 1 over ln of 2, what you have inside is that t approaching infinity, 2 to the x, no, 2 to the t minus 2 to the 0, which is 1. So now when you plug in and you see when t approaching infinity, you're going to have 2 to the infinity, which is infinity. So this integrand, this integral already diverges. So your immediate conclusion is that you don't need to take care of the other one. You don't need to take care of this second integral. So you're going to say this is divergent. So you're going to have your big integral also diverges. You see what I'm saying here? Okay, so first one is pretty easy, nothing challenging with the integration part and the numbers wise. So let's go to the next one. So here you have from 0 to 1 x squared ln of x. So if it was before midterm 1, then you guys, the first thing you're just going to use integration by parts and solve this. But then here, when you actually see the boundaries, the things that you have to check. So as x equal 1 and x equal 0. So this continuity here is going to be at x approaching 0 because ln of x is not defined at x equals 0. You have ln of x approaching 0 plus, but you never have ln of 0. That is not a thing. So what you're going to do here is that x squared ln of x dx. So I'm going to write as limit of t approaching 0 plus from t to 1 x squared ln of x dx. So the next step in this part is after you rewrite the improper integrals is that when you have to take the integral. So I'm just going to go quickly with x squared ln of x dx. So we have u equal ln of x, du equal 1 over x dx, dv is x squared dx. Then you have v is x cubed over 3. Then you're going to have x cubed over 3 ln of x, multiply x squared over 3, take the integral, dx, which is going to give us x cubed over 3 ln of x, this x cubed over 9, plus c. But if you plug it in here, you don't need the plus c because it's a definite integral. So you're going to have x cubed over 3 ln of x minus x cubed over 9. And you plug in 1 and t. So when you plug in 1, what you have here is 0. ln of 1 is 0, and then you have minus 1 over 9. Then you plug in t, which is, I'll write it down. So you're going to have is equal negative 1 over 9 minus limit of t approaching 0 plus of t cubed over 3 ln of t minus t cubed over 9. So as t approaching infinity, this part is as t approaching 0 plus, this t cubed over 9 is going to be 0. So what you have is negative 1 over 9 minus limit of t approaching 0 plus t cubed ln of t over 3. Now if you notice, so you have to find the second limit, right? But if you plug in 0, you're going to have 0 multiply negative infinity. So guess what? This is the indeterminate form, and you're going to do another part of indeterminate form separately. So now we're going to do it. So we have limit of t approaching 0 plus t cubed ln of t. I am going to ignore the 3, because then when I plug in, I'll just plug in and then multiply 1 over 3 again. So it's like simplify the algebra that I have to deal with. So let's see, we have just want to check my number is right. I'm pretty screwed with numbers wise. Okay, so we have, this is 0 multiply negative infinity. So first you have to put it into the quotient form. So you're gonna have limit of t approaching 0 plus. And as like a matter of experience, I would highly recommend you guys, if you have a polynomial, multiply ln. Put ln in the numerator. Do not put it in the denominator, because it's gonna make your life taking derivative very miserable. So you're gonna have 1 over t cubed. Or I can rewrite as t to the negative 3 is up to you guys. So now I'm going to take the Hopital rule. So, oops, what's just happened? T approaching 0 plus. So take derivative, you're going to have 1 over t. This is t to the negative 3. So I'm going to take negative 3 over t to the negative 2, which is going to give me 0 plus 1 over t divided by negative 3 over t squared. So what I end up having is t approaching 0 plus t over negative 3. Very simple, but then it's just going to give me 0, because it's going to be 0 plus over negative 3, so it's just going to be 0. So from that, now you plug it back in here, which is going to give me negative 1 over 9 minus 0, which is just going to be negative 1 over 9. So that is my final answer. So this is kind of like the thing that you should expect in the exam, when it's gonna involve at least 2 things, but it's use everything that you learn in your knowledge. So things in midterm 1, you guys should know it by now and be able to apply the indeterminate form that we just learned from 6.8. So before I proceed to example 6, is there any questions so far? Sure. Okay, so are you good with this example? All right, at 0. Okay, so I'm gonna go ahead to example 6. So here, I would like you guys to have like a moment to do this one on your own, because like I want to take a break. So yeah, I'll give you like a minute or 2 to work on this, and we'll be back to see what you guys get. Okay, so let me mute myself really quick. Yep, you can put your answer, maybe like just like a number, whatever you have there. Okay. You don't know how to do it? Are you being sarcastic or just like you don't know how to do it? Yeah, I have like a second feelings that you guys actually know. Which is pretty funny right now because I'm looking at my notes and I don't have the answer here. But we can go through it together really quickly. I think I took it out of my... Sure. Okay, we're gonna go through it together. Using integration by parts. What? Yeah, I don't think it's right so far. First of all, what did I say about integration by part last time when we do midterm 1? Integration by parts is only for you when you have two different types of functions. So say log and polynomial, or like trig and log, or like trig and exponential, right? So here, what do you have? W over W minus 2 is a fraction. It's a complete polynomial thing. So as what I say, integration by parts is not for it. Integration by parts is only for it when you have two different functions in the same place. So, okay, I'm gonna go through it. First of all, the way that we're looking at it right now is that we're doing improper integrals and we start to have to check the boundary. So if you look at here, the fraction is not defined at w equal to 2, which is in the interval of integration. So you're gonna have to put it into two parts. So limit of t approaching 0 minus from 0 to t, w over w minus 2 dw, plus limit of t approaching 0 plus from t to 5, w over w minus 2. Now I'm gonna find each of them individually. I think that might sound right. So sorry, I don't have a number here, but we can do this together. Anyway, let's just work on from t to 5. Again, I don't want to do with, I always try to do with positive number first and not negative number. So what we have here is that we're going to have limit of t approaching 0 plus. So what is the integral of this? Integral of w over w minus 2. I would say the best way to do it is that if you notice the train, if you rewrite this one as, so there are two ways, but I'll do the easy way. The other way is just like way too complicated. But yeah, we have this, rewrite it as w minus 2 plus 2. So when you separate the fraction, which you're gonna have is w minus 2 divided by w minus 2 plus 2 over w minus 2 dw, which is going to give integral of 1 plus 2 over that. Now, this is now easy to find because it's going to be w plus 2 ln of absolute value of w minus 2, and then plus c. So now you can plug it in here. So I will have this, and then we have, so what we have is we're going to have w plus 2 ln of w minus 2 from 5 to t. So when I plug in 5, what I have is 5 plus 2 ln of 3. Then we have minus limit of t approaching 2 plus, oops, w plus 2 ln of w minus 2, right? So here, if we look at, I will put another arrow so you guys can know where I'm going. So I'm going from here to there. So what we have here, when you plug in that, you're gonna have equal 5 plus 2 ln of 3 minus t approaching, not, yeah, t approaching, well, not t, this is should be t, not w, t plus t. Oops, why does this thing just keep flipping today? T minus 2. So when you plug in t approaching 2 plus, you're gonna have negative 2, negative with a plus is negative 2. So now you look at when t approaching 0 plus, 2 plus. 2 plus minus 2 is 0 plus. So this part is going to be negative infinity. So it's going to be negative infinity here. This part is negative infinity with a negative in front is a plus infinity. So this entire thing, what I said, is divergent. So just one of them is divergent. So the first, your conclusion is going to be w minus 2 dw is diverges. So I think let's see who got that. I forgot the name. So Shivanji, you're correct. I think you might take the integral correctly, but then maybe the number wise there is some problem with algebra or something. So yeah, this is what we have is diverges. So the thing here is that know how to take this integral, maybe like doing plus or minus like this. I think you guys kind of like have this intuition if you do in our practice in the partial fractions part. But am I getting it? Yes. Okay, cool. So yeah, so this is what we have so far. And I mean, if you apply it for like this second one, I think the practice here for algebra is like maybe apply, try to find this limit on the left. You find a divergent as well. And so I think example 4 or 5, I also have as diverges, but I only take care of one. So you guys can try with the other one to see, kind of like give it a practice. So that's all we have for 7.8. Now we're going to go to 11.1. So 11.1 is sequence. Let me see how many examples I have. Oh my god. Why did I put... Anyway, good practice. So sequence. So sequence is kind of like the start of like the important part of midterm 2. So midterm 2 is just going to be about a lot about series, but the basic of series is sequence. So we're going to go with sequence first, and then 11.2 when we go with series. So definition, what is the sequence? The sequence is just a set of number written in a specific order. It can have a rule to it, or it can have no rule at all. So that is sequence. Recursive sequence is that when you have the next term in the sequence depending on the previous term. So it's called recursive sequence. We also have a very famous one called Fibonacci sequence. So when you have the term, that term is going to be the sum of the two previous term. So then you have a sequence. So this is the important part that we need to take care of. The sequence is convergent if the limit of n approaching infinity of maybe like the nth term of that sequence exists, and if it's divergence if the limit does not exist or is plus or negative infinity. Now this is a definition and like a conclusion that you have to remember and clarify it, because for series, a convergent series is a different story. So yeah, you just need the limit to exist. It doesn't have to be like any specific number. It just have to be a number. You also have limit law for sequence. So say if you have like a sum or difference of sequence, then you can use these property to make them work. You also have some other concept called monotonic sequence, is where it only increasing, like all the terms only increasing, or all the terms just decreasing. Or bounded sequence. So bounded sequence is where your series is bounded between a big, like you have a cap, and then you have like a minimum limit. So you have like a ceiling and a floor. So kind of like you hold them together. We also have something called the squeeze theorem for sequence. So if you have, it's very similar to our original squeeze theorem. So if you have a sequence squeeze, like an expression of a sequence squeezed between the other two, and if the limit of n approaching infinity of the other two are L, then the thing in the middle is also L. So it's pretty, if you understand the original squeeze theorem, this one should be very easy. You also have another theorem saying if you have limit of n approaching infinity of absolute value of an, so the nth term of that sequence approaching 0 as like as n go to infinity, then you have the limit of n approaching infinity of an is also 0. Or another way to say that is that every bounded monotonic sequence, oh no, not another way to say it. Another theorem we need to know is like every bounded monotonic sequence is convergent. So very clearly on the graph is, let's say if you have, so it's bounded, so it has a cap and a ceiling, and it's monotonic, so it's only increasing or only decreasing. So you can look at here, it has a cap and the denominator and the thing here. So you can see the fact that it's only in between these ranges. So as n going to infinity, it's gonna approach a value, but it will never exceed it. So it's so that's how it looks like on the graph, and I think it's an easier way to remember this theorem. Other things is like, say you have this part r to the n. So this is where you're gonna learn next week when you call something called geometric series. But when we're talking only about sequence here, so we only care about the terms. It's like the terms in that sequence. So you're gonna have like r to the n. So say you have gonna be like, the sequence is going to look like this: 1 over 2, 1 over 4, 1 over 8, 1 over 16. So it's basically just like 1 over 2 square, 1 over 2 cube, 1 over 2 fourth in the sequence. So this sequence is going to be converges to 0 if the absolute value of that factor that you do, like this is 1/2 here, is smaller than 1. It converges to 1 if that factor is 1. So it's going to be just 1, 1, 1, 1, 1, 1, 1. And it diverges if that value, like absolute value, is bigger than 1, or r is smaller than or equal to -1, or r is bigger than 1. For r equal to -1, it is diverges because it's going to be fluctuating between -1 and 1. So it never approach a number, even though it's bounded in between negative and 1. That's why we say it's diverges, because it's not approach a number. So that's all of the theory that we have. Like a lot of stuff to remember, in my opinion. But if you do practice, these things just like come along into your brain. So let's start with example 7. Determine if a sequence is convergent or divergent, and if not, if yes, determine if it's converged, where it converges to as n approaching infinity. Now, so this is the expression for the n term. So basically the thing that you have to find is find n approaching infinity, 1 over 2 to over n to the 2 to the 2n. Now, what you have here is that, so let's plug in infinity. You're gonna have 1 to the infinity. Aha! Then you have indeterminate form. I feel like you guys are gonna get sick of this so quickly. Okay, so we're gonna put it into a product first and then a quotient. So let's do this. A limit of I know, like you. There's one thing that you have to see about my practice problems. It's always harder than the exam. But if you survive my practice problems, definitely you're gonna survive the exam. So yeah, just think of it as a good practice for you guys. So now we're gonna do n approaching infinity. What we have here is you take that 2n out, ln of 1 minus 2 to 2 over n. Now I'm just gonna find the limit individually. Limit of n approaching infinity. You have ln of 1 minus 2 over n divided by 1 over 2n. Now we take L'Hopital rule. So from here to here, I rewrite it as, I'll take just the limit on it all, and then I rewrite it as a quotient. So 2 steps in 1. Not this one's going here. And then I take L'Hopital rule. So let's see where L'Hopital rule is taking us. So you're gonna have derivative of 1 minus 2 over n is going to be 2 over n squared divided by 1 minus 2 over n. And this one is 1 over 2n. When you take derivative of that, it's going to be negative 1 over 2n squared. So let's do some algebra here and make it look easier to see what's going on. So 2 over n squared, and then you divide it by 1 over 1 minus 2 over n, and then you have divided by this, and then it's gonna be multiplied negative 2n squared. So this n squared and n squared cancel out. So what you have here is gonna be negative 4 divided by 1 minus 2 over n. Now things is easy because when you plug in n approaching infinity, this part is 0. So negative 4 over 1 is going to be negative 4. So when you put it back here, it's going to be e to the negative 4. In any cases, how bad it is a number. Therefore, you conclude that this is converges and it converges to e to the negative 4. It's still a number, which is good. So I would say it's not challenging. It's just a little bit annoying if you wasn't expecting indeterminate form limit at all, and then you see it. But yeah, it's not challenging. Just notice the fact that if you want to find if a sequence is convergent, this is the expression that you have to find. So basically, just find the limit of n approaching infinity of the n term in that sequence. Where did the free go? Oh, the free is just like that sequence started from the third term. So say you start plugging in n, you start the first term in that sequence is when you plug in n equal to 3. But it doesn't really matter because yeah, the way that we write it is from 3 to infinity, which is just mean that the first value that you plug in that sequence is going to be 3. So say here, if you plug in, the sequence is going to go like this: 1 over 2 over 3 to the 8 to the 6. Then you have 1 over 2 to the over 4 to the 8, and then 1 minus 2 over 5. So this is going to be how the sequence go to the 10. So the 3 doesn't really matter. When you try to find sequence convergence, the thing you care about is as n approaching infinity. Is that clear? What's the 1 to the infinity? Oh, 1 to the infinity, the way that I note it there is just like your note to yourself that you're going to use the Hospital rule there. So as I mentioned at the beginning of this session is that if you want to use the Hospital rule, the first thing you always have to check is that it has to be in one of the indeterminate form, and 1 to the infinity is one of the indeterminate form. So it doesn't have any meaning. It's just like a note there that I make to myself that I'm going to use the Hospital rule there. Is that good? Okay. So if we clear here, and as Kyrie said, I'm going to post the slide on, or yeah, I will send the slides to Dr. Kasher so that she can put it on Canvas so that you guys can take care of it. As long as you guys follow what I'm doing, it should be good. If you're missing one note, some note, don't worry about it. You can always rewatch this video or like look at the slide that I put on. Now let's go to example 8. Determine if a sequence is convergent or not. And again, as I say, the thing we care about is n approaching infinity of n factorial over n to the n. And this is, in my opinion, one of the hardest expression, because the concept of factorial and n to the n is very confusing to a lot of students. But if you understand the definition of factorial, then you're going to be in a good shape. What happened is here, when you have n factorial and n to the n, it's kind of very abstract. So the way that I usually do it is that I'm going to write out, okay, what exactly is a factorial? So you have n, multiply n minus 1, multiply n minus 2, multiply until you have 1. Divided by n, multiply n, multiply n, multiply until you have n. Now, at n approaching infinity, very clearly you can see this is a very huge number and a very huge number, so it's also infinity over infinity. But here, you cannot take the Hospital rule, as I say, because do you know what derivative of n factorial is? I mean, I myself, I don't know. You can find the derivative of n to the n using log differentiation. But for n factorial, I have no idea what it is. And it's like advanced calculus. And I really don't want to know that, especially when they're just all in all computer. So what happened is that we're going to use the definition of factorial to solve our problem. So you can cancel out one n here. That's first of all. Then you're going to look at each individual fraction here. So if you look at the terms, it's going to go like in that fraction is going to go like this: n minus 1 over n, multiply n minus 2 over n, multiply n minus 3 over n, until you have 2 over n and 1 over n. Now if you look at this, at n approaching infinity, right? This one is going to approach 1. This one approaching 1. This one approaching 1. But if you look at these approaching 0 and these approaching 0. Why? Because 2 over infinity is 0 and 1 over infinity is 0. Now you have a lot of 1 multiply a lot of other 0 as well. So what happened is that you're going to have 1 multiply 1 multiply 1 multiply 0 and 0. So you're going to have, it's just going to be 0. So your conclusion here is that the sequence converges to 0. So the note I want to make here is that understand the concept of factorial. What exactly is it? And then be able to see the fact that you cannot use the Hovital rule here, just simply because of the fact that you don't know what's the derivative of n factorial. But there's another way to resolve that if you just make note to this. So at n approaching infinity, these things approaching 1, 1, 1, 1, and then you have a bunch of 0. So if you take a product of that, it's going to be a 0. So is it clear to everyone for this example? It is good that you guys seeing it here. The first time I see this problem is in my quiz, and I was just like freak out. Just let me know if you don't understand something. But okay, so no one actually say anything. I'm gonna go to the next example then. How did you get 2 over n1? Oh, so the question of, like, there's a 2 here. So the factorial goes as n factorial equal n multiply n minus 1 multiply n minus 2, multiply every single number smaller than n together. So you're gonna have multiply until you have 3, 2, and 1. So that's where I have the 2 over n and 1 over n, because you're gonna have a lot of n down here, which is gonna match with the exact same number of terms in the numerator. Because for n factorial, you're gonna have n kind of terms here, but each term are different. But n to the n, you're gonna have n terms as well, but you're gonna have all of them in the same. So n to the n is gonna be n multiply n multiply n multiply n, n, and n. So what happened is that I just break them down into each individual fractions. You see what I'm saying? Yeah, until 1. Yeah, you don't go to 0. So yeah, that's what we have. And then let's go to example 9. Last one. Yay! So oh my god, it's like a horrible sequence, but it's a very easy one, don't worry. So again, same questions, but look at this way, it's kind of very abstract for me to understand, especially when you have 2 different functions in it. You have power, and then you have cosine. So the way that I usually make sense of this, and I think it really helps, is that you try plugging in some of the numbers and see what exactly are they, like what is the train, and kind of like give us an idea. So I plug in n at 1 and then 2 first. So you have n 1, 2, 3, 4, 5. Let's see. You plug in 1, so you have negative 1 square, which is 1, plus cosine of pi. 1 plus cosine of pi, which is going to give me 1 minus 1, which is 0. If you plug in 2, you're going to have negative 1 plus cosine of 2 pi, which is going to be negative 1 plus 1, which is also 0. And if you do the rest, it's going to be 0. So you don't even need to care about anything else. Your conclusion is that immediately it's going to be converges to 0. And I actually learned this from my, when I take 141, is that I was given this in one of my homework and I haven't figured it out. So I have no idea what this thing looks like. So the first thing I did is plug it in, and it gave me a sense, and I just come to a conclusion that way. So sometimes the lesson here is that sometimes you see a sequence, you have no clue what the hell is going on in there, especially when you have 2 different types of functions, like power and cosine, or like maybe log and plus something, like a sum of 2 things. Then I would say maybe try plugging in some number and see if there's any train to it. All good? No, it's not like I want it to be over, because today is like a very important day for me. It's the last day I have in Australia, Melbourne, as an exchange student from Penn State. So I have to move out, and I have to take my flight, and I have to clean up and return the room and everything in the same day. And I also have to like go to farewell meeting with my professor. So it's like a lot of things going on, and I'm just like really stressed right now. And I just finished my exam yesterday. You should see me like stay up all night packing up. So yeah, so that's what we have for today. And in my opinion, it's a little bit long, but yeah. So keep going through them and do the practice problem in the book. In the book, I feel like it's kind of easy, but it's a good start. So if you're not like familiar with the concept yet, try the one in the book before trying my practice problem, because there was a lot of things going on in my practice problems, but they're gonna prepare you for the exam. Trust me. So with that in mind, if you don't have any further questions, yeah, thank you for wishing me luck. I'll see you guys next week. Have a great week, guys.